everyone. Today we're going to go over Semester 1 Chemistry Review. Now, as you've probably noticed, chemistry builds on itself. So it's important to take stuff that we learned first semester and we're going to see it be carried over into things that we're learning second semester. It's important to make sure we have this baseline and an understanding so you guys can be successful. Also, if you're one of those students who at the end of the semester just threw away all of first semester stuff, this has stuff in it that you are going to need moving forward as well, such as your tables and your charts. So let's go ahead and get started. Let's start at the baseline. Let's go back over what exactly is chemistry. What are we studying? Chemistry is the study of the composition of matter. So let's break this down. Composition. That means what is something made up of? What elements make up, for example, ammonia? And we're going to talk about changes that happen to different materials or matter. Just to simplify and go over what matter is, it's anything that has mass and occupies space in our universe. So basically anything physical that we see and we can hold and feel, such as the wind in our universe. One thing that is not matter is light. Light is actually considered energy. Now, a property, we're going to talk about that a lot as well, are characteristics that allows us to distinguish a type of matter from another. It's anything that you use to describe an object, such as its mass, its boiling point. Properties also include its smell, taste, is it catch fire easily, texture, any description of it. Now, also, true or false, chemistry affects all aspects of life and most natural events. And the answer that you should circle in your notes and know is true. Chemistry is an integral part of our lives. We use it every day without even realizing it. Chemistry also is what runs our bodies. It keeps processes going. So it's important to understand and help study that. Now we're going to delve into how can we talk about the composition of matter. And we can actually classify matter into 3 states, and they are solids, liquids, and gases. If you were in integrated science, you learned 2 others, but these are the 3 that we deal with on Earth. They are solid, liquids, and gases, and we can classify them based on shape or volume. Solids, we say that they have a definite shape and a definite volume, which means their shape and volume doesn't change if you move locations. Liquids, on the other hand, are slightly different. They have an indefinite shape, so their shape actually changes, and we see this. Liquids can be spilled on the ground, they can be put into the shape of a glass, they can also be added to a bowl. However, the volume doesn't change, the volume stays the same. Gases, however, are both indefinite shape and volume, so their shape and volume changes based on the container that it's in. It either expands to fill a room, or we can actually compress it. That leads into the next thing. Can it be compressed? Compressed means that we're taking those particles in these states of matter and pushing them closer together. Now, solids and liquids are not very easily compressed because those atoms are already pretty close together. There's not that empty space to push them even further together. While gases are so spread out, there's a lot of space in between the atoms, and so we can easily push those atoms closer together and condense that gas. So we see compressed gas all the time in movies such as scuba tanks, but also if we think of going to the store and seeing helium tanks to fill balloons. Last but not least, they each have their own color on the periodic table. My periodic table in my classroom represents this. If you see something that has black lettering, it's a solid. If it has blue lettering, it's a liquid. And if it has red lettering, it is a gas. Now there are 2 liquids, and so these ones I kind of require you to know. The first one is mercury, which is Hg, and the other one is bromine, which is Br. Now, in terms of classifying matter, there are three categories you can put them in. They are element, compounds, and mixtures. An element cannot be broken down into simpler substances and still retain its identity. We say that it's made up of one kind of atom. Whereas compounds are composed of two or more elements, and these are chemically combined. And what that means is that these are essentially bonded together, they're held together. Mixtures are going to be still two or more elements or substances, but they're not bonded like in compounds. They're just kind of physically combined, kind of just free floating mixing. All of the substances a mixture still retains its own identity. Now, with elements and compounds, we use different things to represent them. Symbols are used to represent elements, for example, C for carbon, Fe for iron, and Mg for magnesium. Please note, last semester I marked off if you did not use correct capitalization. I will do the same thing this semester. Remember, first letter is always capital, second letter is always lowercase. This is important because when we get to formulas, formulas combine two or more elements. Water, for example, is represented by H2O, and carbon dioxide is CO2. You also have carbon monoxide, which is CO. So CO, both capital letters, is carbon monoxide, which is a deadly gas that if you breathe it in, it causes fatality. And then you have CO, and this is an element. This element is cobalt. So there's a difference. One's a compound, one's an element. Now, one thing to note out is that these chemical formulas tell you the type and number of atoms that make up this compound. For example, water, it tells me it's made up of hydrogen and oxygen. We have 2 hydrogen and 1 oxygen. Now, in terms of mixtures, we can actually divide these even further and talk about 2 types of mixtures, heterogeneous versus homogeneous. Now, if you look at their prefixes tell you about them. Hetero, if you hear that prefix is on any words, there's some in biology, this means different. And homogeneous, this means they're the same. So heterogeneous means if you have a mixture, you can see the different parts of the mixture. If you have chicken noodle soup, you can see where the noodles are, the chicken, and the broth. Homogeneous mixtures, these look the same throughout. A good example is bronze is made up of tin and copper, I believe, and you cannot see those individual elements, but they are just melted together. Now, properties, there are 2 types. There are physical properties and chemical properties. And remember, properties are used to distinguish among things. Physical properties are said to, we can look at a sample of matter and observe these properties, but it doesn't change what that substance is made up of. These include color, odor, density, melting, boiling point, hardness, and solubility. For example, if I talked about boiling point, if water boils, it doesn't change what water is. It's still water vapor. Chemical properties, though, is that when you observe these properties, they're going to change. These include if they're flammable, if they catch fire easily, if things rust, corrosiveness, reactivity. For example, methane gas, if you burn it, it creates a completely new substance of water and carbon dioxide. Now, physical versus chemical change. This is when we're taking these properties and we're actually performing them. We're causing a change. Physical changes the substance, such as the shape or the color, but it doesn't change the composition. So we don't have anything new. Chemical, though, causes a completely new substance to be made. So how do I know if it's physical versus chemical? Physical is going to change the shape, such as cutting a piece of paper in half, or taking Play-Doh and making it into a heart shape. It also changes the size. You can change the state of matter, so if you take something and you freeze it or you melt it. And then diluting and dissolving means are you putting it in water or something else that will dissolve it down. Chemical, often if you see anything burning or cooking, if a light is produced, often if you see bubbles being made, that means gas is happening. Sometimes there's a color change, but color change can also be physical as well. Rusting, or if you form a precipitate, and all that means is it's a solid that forms when you mix two liquids. Moving on from properties and how to classify matter, we're now going to talk about the structure of an atom. And we've started small and we're slowly building up. So, structure of an atom is made up of 3 subatomic particles. Sub meaning littler than an atom. They are proton, electron, and neutron. And electron is going to be the most important one for this semester. Let's just go through them all. We're going to look at them based on charge, location, and their relative size. Protons are positive while electrons are negative, and then neutrons are neutral. In terms of their location, protons and neutrons are in the nucleus. Now remember, the nucleus is in the middle and it's positively charged because of these protons. While electrons actually orbit around that nucleus in orbitals. And then in terms of relative size, these two are about the same size, while this one is a lot smaller. The electron is a lot smaller. Also, when we're learning about atoms, we learned these terms, and these terms are going to pop back up. For example, atomic number. Atomic number is the number of protons, and this is actually unique to each element. Now, I'm actually going to skip down here to the bottom because atomic number, some people say is the number of electrons, and in a sense, that's half true. If the atom is neutral, which means it has no charge, oftentimes your electrons equal protons. But this semester, we're going to talk about how we can have an element, but they have different number of electrons. Then we have mass number. Mass number is the total number of protons plus neutrons. So we're adding those two together, and we can actually take that information and realize that we can figure out neutrons if we take our mass number minus atomic or mass minus number of protons. So here I have a periodic table because I'm going to refer to it as we walk through these examples. So first thing, atomic number. In order to find the atomic number, we need to look at the periodic table. If we look at this, all periodic tables generally have a key up here. So if we look at this key, it says my atomic number is in the top right-hand corner. And that's where they are on my periodic table in my classroom. So here, iron's atomic number is 26. If we were looking at the ones we have on your paper, one of the first ones we have is carbon. If we look, carbon is up here, and we can see that its atomic number is 6. So we're going to go ahead and fill that in. Iron, we just did that one, that's 26. And then we're going to go back and find oxygen. So oxygen's over here, and it's 8. Now, if we remember the definition for atomic number, that is the same as the number of protons. So these have to match. So this one should be 12, this should be 26, and then this one should be 8. Then, if these were neutral atoms, which they are all neutral, protons should equal, so they equal for neutral atoms. So protons are 6, electrons should be 6, and vice versa. Okay. Now we have these other two fields. So we have to look back what we have. If we have mass number, let's fill mass number in first. and go back and see that mass number is going to be protons plus neutrons. Now, oftentimes people confuse it with this number up here. That is not mass number. This is atomic mass. It's the most stable mass number, but it's not the only one. So this is atomic mass. It's an average, while mass number is going to be a whole number. So don't refer to this, not the same thing. You want to actually follow the rules and do 6 plus 8, which is 14. And then here, 8 plus 8 gives me 16. Now we have left is to find neutrons. So neutrons, if we go back, is mass minus atomic. So if we look at this, 24 minus 12 gets me 12. If I look at 56 minus 26, you get 32. Now, in terms of different types of atoms, there are isotopes and ions. These are the same type of atom, but they're different slightly. For example, isotopes, they have different number of neutrons. And since neutrons has a pretty heavy weight in the atom, it also affects their mass as well. So atomic mass, remember, this is our weighted average mass of our isotopes, or the weighted average of all the mass numbers. Now, ions, again, still the same atom, but instead of different number of neutrons, these have different number of electrons. This is super important going in because we're going to be talking about ionic bonds and ionic compounds, and they're made up of ions. So ions have different number of electrons, and typically electrons equal protons, so it's a neutral atom. But if we lose or gain an electron, that's going to actually affect our charge. We're no longer neutral. We're either going to be positive or negative depending on what happens. And we learned two terms for these ions. There are cations, these are positively charged, and there are anions, which are negatively charged. So we're going to hit back up on all of this in chapter 7. And typically we're going to see that certain groups of elements form cations and certain ones form anions. For example, metals tend to be positive and nonmetals tend to form negative ions. And then to wrap it up, we're going to talk about electron configurations and then how to classify metals, nonmetals, and metalloids. So electron configurations is something we covered in chapter 5. We're going to bring that back, and instead of doing electron configurations for a neutral atom, we're going to talk about how do we write them for ions. So remember, the first part, 1, tells me my energy level. This part down here tells me my type of orbital. And remember, we can have an s orbital, we can also have a p, a d, or we can have an f. And then up here, this tells you the number of electrons that fit in this orbital. So for example, S can hold 2 electrons, P can hold 6, D can hold 10, and F can hold 14. I've also added this. This was in your guys' notes and in the lesson when we went over this chapter. I love this graph because it shows so much. It shows you our energy levels. So remember, your principal energy level is usually equal to your period number. And this also tells me my type of sublevels. So if you are an S, you have 1 orbital, and then like we talked about, 2 electrons. If you are a P, you will always have 3 orbitals and 6 electrons. D will always be 5 and then 10 electrons. And then F will always be 7 orbitals and 14 electrons. I've also included this. You colored this last year. You guys got to use it on your test. You got to use it on your final. It's very awesome. It helps you write those electron configurations. Just make sure you read it like a book. So for example, if you wanted to write the electron configuration for this element that sits right here, you're reading left to right. 1s, and there are 1, two of them, so 1s2. Then we go to the next line, 2s, and there are two boxes there, so 2. Here's my 2p, and if you count the boxes, there are 6 boxes there. Then you go to 3s, note there are 2 boxes, and then you go to 3p, notice that there are 6 boxes, and then you go over here to 4s. Now note I circled the second box, so 1, 2, 4s, 2. Now the periodic table, we're also going to be using that a lot. Periodic table is defined as the arrangement of elements in which the same elements are separated into groups based on repeating properties. This periodic table is going to be organized based on atomic number. And we have groups versus periods. Groups are vertical, up and down. Everything in a group tend to share similar chemical properties because they have the same number of valence electrons. And that's going to be important. We talk about it coming up. Now, group A elements, these are your representative elements. Their number is going to equal the number of valence electrons. So, for example, chlorine is in group 7A, so it has 7 valence electrons. Calcium is in group 2A, so it has 2 valence electrons. The only exception is helium. Helium is in group 8. It's considered a noble gas, but it doesn't have 8 valence electrons. It actually only has 2. Periods, these run horizontal, and here all elements in the same period have the same energy levels. And the number of valence electrons increases by 1 for representative elements as you move left to right. And here we're going to talk about metals, nonmetals, and metalloids. I said understanding the periodic table is important, and periodic tables actually help show where metals, nonmetals, and metalloids are. For example, we're going to start down here with metalloids. These have characteristics between metals and nonmetals, but I'm starting with these because this is our stair step on our periodic table. In my classroom, I have them color-coded with green triangles in their corner. Then you can ask yourself, if I know where the green triangles are and I know those are metalloids, I just have to see who's left and right of that stair step. For example, metals, which are good conductors of heat and electric current, most of them are solids. They're very ductile, which means you can draw them into wire, and they're malleable, which means you can bend them. These tend to be to the left of the metalloids, so left. Nonmetals, which are poor conductors, most of them are gases, and if they're a solid, they're pretty brittle, tend to be to the right of those metalloids. So again, as long as you know where the metalloids are, look left, look right, and that will tell you. So here's the picture I have. Again, here's your stair step for your metalloids. Note that everything to the left, except hydrogen, are metals, and then everything to the right are going to be nonmetals. And then I've also included this because even though I did have the earlier picture, this has been used in your lessons, and I just want to make sure you have access to the electron configurations and them groups. So you can see who is the S block, P, D, and F. Any questions, please make sure you email me, and I hope you guys have a great day. Oops.